Alright, so in this video we're going to start exploring a different way to calculate volume than what you have in the past. This is going to be one of our many applications of integrals. So just as a heads up, I'm not going to show a lot of the visual representations in these problems due to just a general time constraint. If I showed all the visual representations of these problems, we could easily add on 30 minutes to this video. However, you can check out a ton of visual aids in Dr. Phil Yaskin's book. He's a professor at Texas A&M, which is linked on my website, and it's free. You just need to be a Texas A&M student. There's also tons of other resources online, such as GeoGebra and others, where they will show you stuff like cross sections given a base, and also solids of revolution, which is what we're going to be discussing in 6.2. So first, I want to give the definition of volume from a calculus standpoint. We're going to have S being a solid, right? So here's our solid S, right? It's this blue thing right here. And it's going to lie between two x values. So it's going to lie between x equals a and x equals b. Now I know it looks like it sticks out past b, but that's because this is a three-dimensional solid sitting in a two-dimensional plane. And so when I say two-dimensional plane, I'm saying we're in the xy plane. And we're going to have a sub x be some continuous function. Right, so that continuous function is shown right here. Here's a of x. Right, we're going to commonly use this, but it's written as a subscript right here. So this is a continuous function, and what it represents is it represents the cross-sectional area of S in the plane P sub x through x and perpendicular to the x-axis. So let's see what I'm talking about here. What I'm talking about here is we have this plane P sub x, right? And we have intersected it with this solid S. When we intersect these two, what we get is all of this red or pink, whatever you want to call it, all of this area in here. And so a of x is going to represent the area of that red area. And notice that this plane P sub x, we say it's perpendicular to the x-axis, because when we run this down into the x-axis right here, we get a 90-degree angle right here. All right, and then the volume of S is going to be given by this infinite sum, which is equal to an integral. So let's look at why we're calculating this infinite sum. The reason we're calculating this infinite sum is because what we're going to do is we're going to take infinitely many of these red areas. Right, so we'll have another one right here, and this is going to look awful. I apologize for that, but it looks something like that. And we'll calculate the area of it and add it to the other one that we already have. And then we'll take another one right here. Okay, we'll calculate the area of it and add it to our other two areas. And the goal is, these are like slices of our solid. We're slicing through with this plane. We're getting some two-dimensional object. We find the area of it. And what we want to do is take a slice at each and every point in our solid. And then we add all of these areas up, and that will give us the volume. Right? So you can think of like a cylinder as basically just stacking infinitely many circles on top of each other. Within some x bounds. Right, so if we laid a cylinder flat right here, that may look something like this. And then what I'm doing is just taking infinitely many circles in here, finding the area of all those circles, and adding them together to get the volume of this cylinder. That's kind of what we have going on right here, or it is what we have going on. It's just a weird shape. Okay, and then this infinite sum is going to be equal to the integral from a to b of a of x. Okay, and so here's another picture right here. If you want to look into what, right, in this infinite sum above, what is delta x? What is this x sub I star? X sub I star is in some interval. We have an x sub I minus 1. We have an x sub I. And then x sub I star is going to be the point in the middle of those two. And so what we do is when you have this interval from x sub I minus 1 to x sub I, it gives you this solid piece right here. Right, and going all the way around, and then back up, all the way around, and then back up, right? So it gives us that solid piece, and we choose x sub I star as our slice in here, right? And so this a of x sub I star is going to be the area of the slice at x sub I star. And so you can see over here, what's happening in this picture is we've taken 1, 2, 3, 4, 5, 6, 7 partitions of this solid, right? And what we want to do is basically break it up into infinitely many. That way we're capturing two-dimensional pieces, adding their areas together to get this volume. Okay, so let's think about this in terms of finding the area of a sphere. Well, for finding the area of a sphere, or sorry, this should say, I apologize for this. This should be volume of a sphere. So we know that the volume is given by V equals 4/3 pi r cubed, right? That's a previously given formula to us. We've been using it whenever we're asked to calculate volume in geometry and stuff like that. And we're going to have r is the radius of this sphere, right? So the radius of a sphere, we take, if we're centering the sphere at the origin, then we take the center and we extend to the boundary, right? So we just take some point on the boundary, so maybe like this point. And then the radius is going to be the distance of this line. Okay, but now we want to prove that this formula is true, and we want to prove that it's true with calculus. Okay, so our cross section here is going to be a circle, and the radius of this circle is given by this line, right? Now, this right here is some point x comma y, which means that the length of this line is going to be equal to y. So that tells me that the area of the circle is going to be, sorry, so we have a of x, right? And so you say, okay, well, what's the area of a circle? That's going to be pi r squared. And we said the radius was y. So then that gives us pi y squared. Sad face. The reason I put a sad face here is because we want an a of x function, but our variable here is y. So what we need to do to this is we need to find some way to substitute out this y and bring in something where our only variable is x. And here's how we're going to do that. We can make a triangle right here. So let me bring this triangle out to the side where maybe we can see it a little bit better. So this, what I'm drawing or trying to draw right here, is the same triangle as what I'm pointing to. So this has a hypotenuse of r, a height of y, and a base of x. Okay, well, by Pythagorean's theorem, we know that r squared is equal to y squared plus x squared. And so now if I subtract x squared over to the other side, I have something to plug in for y squared in my a of x formula. So this is going to be r squared minus x squared equals y squared. And now someone's saying, okay, but you said the only variable we wanted to put in our a of x function is x. And this is okay because r is not a variable. When we made this sphere, we chose some radius r, some number, hopefully bigger than 0, right? Because I don't want to calculate the volume of a point. And we're leaving it, right? So I could choose the volume to be 4. I'm leaving that radius at 4. It never changes anywhere on the sphere. And so then plugging into our a of x function, we get that a of x is equal to pi times y squared, but y squared is equal to r squared minus x squared. And so this tells me that our volume is equal to the integral from a to b, where a and b are our smallest and biggest x values respectively. So that should be negative r and r of a of x. So that should be pi times r squared minus x squared dx. Okay. So now what I want to notice is that r squared minus x squared, that's a constant minus x squared, right? So all this is some downward facing parabola shifted up r squared units. So this is an even function, right? And so we can apply our rules about even functions, which says that this becomes 2 times the integral from 0 to r of, now what I'm going to do is this pi is a constant, so I'm going to pull the constant out, of r squared minus x squared dx. Okay, so this is equal to 2 pi times, let's see, r squared is a constant, so the integral of that would be r squared times x minus x cubed over 3. So this should be 2 pi, and then we're going to have r squared times x, but we're plugging in r for x, so this is r cubed minus, we have x cubed, but we're plugging in r for x, so that's going to be r cubed over 3. And now we don't need to plug in 0, because when we plug in 0 for our x's in here, we're just going to get 0 everywhere. So this is 2 pi times, let's see, this would be r cubed minus r cubed over 3. Well, r cubed is the same thing as 3r cubed over 3. So we can do 3r cubed minus r cubed, which gives us 2r cubed over 3. And so then our answer is 4 pi r cubed over 3, just as we expected to get from up here. Okay, so that is an example of us using integrals and cross-sections to evaluate the volume of some three-dimensional object. Now let's look at another problem, example 1. So for this example, we have a solid S that has a base that is a circular disk with radius 3. So let's talk about what a circular disk is. A circular disk is whenever we take a circle and we include the interior of it. So what I mean by that is we take our circle with radius 3. Right, so it's going to look something like this. I know per the usual I have really good drawing. Okay, and then we shade in all of this inner part to show that this is included in our base, right? So you can kind of think of it as like a frisbee, but this is a two-dimensional object. And now, so now I want to point out something really key. We are being asked to find the volume of the solid if the parallel cross section taken perpendicular, this should say taken perpendicular to the x-axis are squares. What you need to key in on is that this is perpendicular to the x-axis. This means you should have a dx integral. Okay, and also, so now I'm going to go ahead and just draw my line, my slice that I'm taking, or at least like the base of this square. Right. So this is a line that is going to be perpendicular to the x-axis. Okay. Now, if this is the base of one of our squares, we want to figure out the area of each square. So remember that a square has side length s on all sides. Okay, and now we wonder, well, what is the length of this green line that I've drawn right here? Well, if this is some point x comma y, then this is going to be x comma negative y, right? Because our circle should be symmetric about the x-axis, which means that each of these two little segments are going to have length y, which means that the entire thing is length 2y. So I should have that s equals 2y, which means that the area is going to be equal to s times s, or well, s squared, and s squared would be 4y squared. Now, our problem is that if we were to just do our integral and plug in our area function, right now our area function is in terms of y, but we want a dx integral. So here's what we're going to do. We can form a triangle. I'm going to form a triangle here. And on this triangle, these would have side lengths x, y, and then this part right here, the hypotenuse, well, this is the radius of the circle, and we were told that it has radius 3, so this should be 3. Okay, let me go ahead just for, I guess, our sanity. This triangle drawn out to the side, this would be 3x and y. So we can use Pythagorean's theorem to say that 3 squared, which is 9, is equal to y squared plus x squared, which means that 9 minus x squared is equal to y squared. So I can substitute in to say that this is equal to 4 times 9 minus x squared. Okay, so now I have an area function in terms of x, which means it's time to integrate. So we're supposed to have that the volume is equal to the integral from a to b, where here a and b are our smallest and biggest x values. So that should be negative 3 and 3, right? Because it's the endpoints of our that's the furthest points to the left and the right on our disk. And then we should have a of x. So this is going to be 4 times 9 minus x squared dx. I can pull our constant out. So this becomes 4 times the integral 3 to negative 3, 9 minus x squared. Now what I'm going to do again is notice that this is an even function. So this is going to be 8 times the integral from 0 to 3 of 9 minus x squared dx. Sorry, I forget that sometimes. Okay, so then this becomes 8 times, let's see, the integral of 9 would be 9x minus x cubed over 3 evaluated from 0 to 3. So this is going to be 8 times 27 minus 27 over 3, which is 8 times 27 over 3 is 9. So that means we have 27 minus 9, which is going to give us 18. And so our answer should be 8 times 8 is 64, carry the 6, and so we should have 144 as our answer. Okay, now let's move on to look at example 2. Example 2 is a little bit harder because our cross sections, I would say they aren't as easy as squares, right? Not saying that squares are easy, but just that triangles are a little bit harder to deal with than squares. So we're given that the solid AS has a base that is bounded by the equations f of x equals x squared and g of x is equal to 4. So just like in our previous assignments, or well, videos, I'm going to go ahead and mark these with colors so I can get an idea of what they look like. Okay, so I know g of x equals 4. Looks something like this, right? A horizontal line at y equals 4. And then f of x equals x squared. Well, that should hopefully look something like this. Okay. So now the first thing we need to pay attention to is that our cross sections are perpendicular to the y-axis, which means this should be a dy integral. Okay. Now let's see what one of these would look like. So if I take something in here, okay, well, this point right here is going to be x comma y. This one would be, let's see, this should be negative x comma y. And so the length of this would have length x, this would have length x, so the length of this entire segment is going to be 2x. So we can get an idea of what our triangle is going to look like. Okay, so we have a triangle here. And we know this base can be split up like this. Well, what's important is that this is an equilateral triangle, which means if this base is 2x, then these are also going to be 2x. And so we need to look at the area of this triangle, which means we need to do 1/2 base times height. Here's our height. Okay, and notice everything I have right now is x's and an h. But we want a dy integral. So what I'm going to go ahead and do is write that x squared plus h squared is equal to 4x squared, right? And that's using the Pythagorean theorem on one of our smaller triangles inside this big triangle. What that tells me is that if I subtract over x squared, we get h squared is equal to 3x squared. Okay, so now that we have h squared equals 3x squared, I'm going to go ahead and try to calculate our area. Even though I know that there's not going to be any y's in there, I'm hoping that once I have a formula for area, we can do something where maybe we substitute in something using our curves. So we have that the area is equal to 1/2 the base, which would be 2x, times the height. So what I want to do here is note that h is equal to plus or minus the square root of 3 times x. because I'm just taking a square root on both sides. Now h is a distance, so there's no need for this plus or minus business. This should just be positive square root 3 times x. Okay, so 1/2 base times height. Well, this is going to be equal to 1/2 times 2, that'll give us 1. And then x times square root 3 times x, that would give me square root 3 times x squared. Now what I'm going to do is we have this green curve which says f of x equals x squared. That's the same thing as saying y equals x squared. So I'm going to use y equals x squared. So let me move this over to the side a little bit. Use y equals x squared to get that. All right, now I'm just, all right. And this is going to give us that a of x is equal to square root 3 times x squared, but we're using y is equal to x squared, so this is just square root 3 times y. Right, now that we have our area function, we can use volume equals the integral from a to b. Now, this time, since we have a dy integral, we're not looking at the smallest x and biggest x values. We're looking at smallest y to biggest y values, right? Again, that's because we're doing a dy integral. We're doing this with respect to y, so we need to find the bounds on y. Well, our smallest is going to be 0. The biggest will be 4. Then we have our a of y function, so we'll have square root 3y dy. So this is going to be square root 3 times the integral from 4 to 0 of y dy. So this is square root 3 times y squared over 2, evaluated from 0 to 4. Which will give us square root 3 times 4 squared, which is 16 over 2. So this is 8 times square root 3 for our volume. All right. Now we're going to move on to our next problems, which are going to be done by finding volumes of solids of revolutions. When we do this, we'll be using one of two formulas, right? So if we have a dx integral, we'll be using this one. And this is going to be whenever we're running perpendicular to our x-axis, which another way of saying that is we're running perpendicular to some line y equals c. We'll talk about this later. And this one is going to be for our dy integrals. Now, we're going to be using one of two following methods in this section. We'll either be using disk or washer methods. If your cross-section is a disk, then we know that the area of that disk is going to be pi r squared. And we'll look at how do you find the radius of the disk. If your cross-section is a washer, so real quick, a washer is something that looks like this. It's like a disk, but we take out some smaller circle, some smaller disk centered in our bigger disk, right? You can kind of think of it, it's like a two-dimensional donut. It kind of looks like that. Okay, and if we wanted to find the area of something like this, then what we need to do is we need to find the area of the big circle. So let's say that this big circle, right, this has radius, I don't know, we'll call it big R, or to be consistent with what we're using over here, I'm going to call this R out. This is the radius to the outer disk, Okay. And then, so if we want to calculate the area of this big disk without the smaller disk taken out, what we would get is we would get pi times r out squared. Now we need to take away the area of the smaller disk that we removed from this. So this smaller disk, right? So if we look at something like this, we're going to call this Rn, right? This is the inner radius. Okay, and the area of the smaller disk, well, that would be pi times Rn squared. And so like we said, we're going to get rid of the, we want to remove this smaller disk, so I'm going to be doing minus, right? And that is how we get this formula over here. An important thing to notice is that we have a pi, we're multiplying both of these by pi. So I can really rewrite this, and what I like to use most of the time is that this is pi times r out squared minus Rn squared. Right? So I just factor that pi out. It makes our integral look a lot cleaner. Okay? And what I'm going to be doing is I'm going to be talking about this thing called a gap. When we know when to use a disk and washer based on whether we have a gap or not. And it may not make sense right now, but hopefully it will in a little bit once we start drawing out some pictures. So this is for number 1, for the disk method. This is when we have no gap. In between our region and the axis of rotation. Similarly, number 2, the washer method is when we have a gap. Between our region and axis of rotation. Okay, so let's look at example 3. We want to find the volume of the solid obtained by rotating the region bounded by the following equations about the x-axis. The first thing I'm going to note is that we are revolving about the x-axis. Okay, so when I draw my xy plane, I'm immediately going to note this. This means I'm revolving about the x-axis. And what it does is it tells me where I take my slice out of my region. Because I'm going to be taking the slice perpendicular to the axis that I'm revolving about. So I'm going to be taking the slice perpendicular to the x-axis. Okay. So, per the usual, I'm going to mark these with different colors. So we know that y equals 0. That looks like this. We know that x equals -1. Well, let's see. If this is -1, then it looks something like this. If I have x equals 2, that looks something like this. And if I have y equals x squared plus 1, well, that would look like, let's see, 1. Something like that. Okay? And so the region bounded by these 3 curves is going to be this region in here. Now here's what I'm talking about by having a gap or not having a gap. This light blue area is our region. Notice that when we compare this light blue area to our axis of rotation, which happens to be this like purple line right there, right? So I'm going to go ahead and use black. There is no gap. That tells me that I should be using the disk method. The integral from a to b of a of x, which is going to be equal to the integral from a to b of pi r squared. And so now we need to figure out, well, how do we get our r? If I take some vertical slice in here, let's say I take my slice right here. So this is my slice. The radius is whatever the length of this slice is. So let's say that this point right here, this is something x comma y. Then the length of this is going to be y minus 0. The reason for that is because it's just going to be the difference of y values from this red dot to this red dot. Well, the second red dot, the one on the bottom, is on the x-axis. So it has a y value of 0. Okay? And we know this y value up here on the upper red dot, that can be represented by y equals x squared plus 1. So that tells me that r is equal to x squared plus 1 minus 0, which is just going to be x squared plus 1. So then our integral becomes v equals the integral from a to b, so that's going to be our leftmost and rightmost x values. So we have 1 here. We know this was negative 1, and this was 2. So it should be the integral from negative 1 to 2 of pi r squared. So this is going to be pi times x squared plus 1 squared dx. Now, a lot of these integrals I'm not going to calculate all the way out. The hardest thing to do on these problems is to set these integrals up. Once you get to here, you're either going to use your integral rules. You're going to simplify as much as you can first. Then you're going to use your integral rules or use substitution, right? Those are our methods of attacking integrals so far. Okay, so right here, when you see something that looks like this, you may immediately think u substitution. Well, I hope you would immediately think that we should pull this pi out, right? It's a constant, so let's pull it out. And now we have to integrate something that looks like this. And so it seems plausible that maybe we do u substitution. Well, a nice way of integrating this, since we don't have crazy exponents going on, is that we can just FOIL it out, right? So this x squared plus 1 squared, you just do the first term, square it, so it's x to the 4th, plus the second term, square it, so 1 squared is 1, plus 2 times the first term times the second term, so times x squared times 1, so just 2x squared dx. Okay, and so then this becomes pi times, we'll have, now we integrate each of these. So this is going to be x to the 5th over 5 plus x plus 2x cubed over 3, evaluated from negative 1 to 2. Okay, and then this will give us, when you calculate this out, this should give you 78 pi over 5. Right, so like I said, I'm not going to be evaluating a lot of these integrals. If I see something that has something really tricky in it, like it's not this foiling method, it's not one of your integral rules, it's not u sub, then I'll go ahead and do it. For the most part, I'm just going to stop right at this point, because I trust that, especially after last week, y'all can finish the problem from here. Okay. Let's look at example 4. So here, the first thing that I want to note is that we are now revolving about the y-axis. So something a little bit different is going to happen here, but it's going to be the same general idea. Okay, so we'll call this green and this blue. Then our graph should look something like, all right, whenever I get something that looks like this, a constant times y minus y squared, or a constant times x minus x squared, or if we need to, we can change that minus to a plus. The trick here is going to be to complete the square. So to complete the square, what I'm going to do, since this has a minus, I'm going to write this. So first I'm just going to rewrite it exactly like it is. I'm going to write this as x equals, I'll put a minus sign out in front since we have a negative on the y squared. And then this is going to be y. And then we have to choose, is it going to be plus or minus this constant divided by 2? Okay, so let's think about this. If I do minus, 2 divided by 2 is 1 squared. Now, when I square this out, I would end up getting a negative 2y. And then this negative sign right here would get applied to it. So that would become a positive 2y, which is what we have over here. So this is the correct thing to write here, a minus. If I had written plus, then we would have a positive 2y coming out of foiling this. And then we would hit it with this negative sign. And so that'd give us a negative 2y, which is not what we wanted. Okay, so this is going to be y minus 1. Now notice that something here has changed, because now when I FOIL this out, what we would get is negative, let's see, we'd have y squared plus 1 minus 2y, which would be negative y squared minus 1 plus 2y. And so this almost looks like what we had from the beginning, except for now I've introduced this negative 1, which means I need to add 1 to this. The reason I have done all of this, the reason I've done this completing the square method, is because now it's a lot easier for me to know what my graph looks like, right? Now I know that this is going to be a parabola shifted 1 to the right, up 1, and opening to the left. Right, so something that looks like that. Okay. Now, if you really just don't like this completing the square method, you can try just choosing, y values 0, 1, 2, plug them into this green equation that we started with, and get your x values from there. However, if the completing the square method makes sense to you, this is a pretty quick way to be able to tell what our graph should look like. Okay, our other curve was x equals 0, so it looks something like this. So then our region is going to be this region in here. Okay, so first off, we're revolving about the y-axis. So I'll draw the symbol in here. It tells me I should have a dy integral. So this is going to be, also, are we using washer or disk method? Well, notice between our region and the axis we're revolving about, there's no gap here. Okay, there's no gap in between the light blue region and this dark blue line. I mean, other than the gap that I can't color in because I'm not good at coloring in between the lines. Okay, so we should have v is equal to the integral Okay, so since it's a dy integral, it should go from lowest to highest y value. So it's going to be from 0 to, this was 2, of pi times r squared. Okay, so we need to figure out what r is. To do that, I take a slice perpendicular to the axis that I'm rotating about. Okay, so this point right here, it's going to be some point x comma y. And so the distance here, this distance is going to be x, because we're going from some point that's 0 comma y to some point that's x comma y. So the distance of this segment is going to be x. Okay, so we can say that this is, our radius is x squared dy, but this is an issue because we're supposed to be integrating in terms of y. So what I'm going to do here, let me backtrack and write some of this out. So we have that r is equal to x, which is equal to 2y minus y squared. I'm getting that from our green formula that we started with, right? I'm substituting in 2y minus y squared for x. So this means that a of y, our area, is going to be pi r squared. So this is going to be 2y minus y squared squared. Okay. So that this should be v equals our integral from 0 to 2 of a of y. So this is pi times 2y minus y squared squared dy. So we can pull out, there's actually a couple different things we can do here. The first thing I want to do is notice that this region, this light blue region that we have over here, it is symmetric about this line, right? When we flip this over, they're exactly the same when we flip over this line. Okay, I'm going to extend it out a little bit so it actually looks like a line. What this means is that we can use our properties of symmetry. It doesn't look like it right now, but let me make it look like it. Okay, so we can pull out this pi. We have the integral from 2 to 0. I'm going to FOIL this out. So this becomes 4y squared plus y to the 4th minus 4y cubed. Okay, so if you just seriously don't believe me, one option is for you to calculate from here, right? Calculate your area. But the trick is, once you start noticing these lines of symmetry, we could have written this as, right, and I can still rewrite it, as 2 times what we have. So this will be 2 pi. And then our integral will go from 0 to 1, right? Because this is where 1 is. And so all I need to do is just calculate this lower half right here and multiply by 2, since it's symmetric about this orange line. If this doesn't feel right to you, if you don't like it, you're more than fine to just calculate from here. You're going to get the same answer no matter what. Okay? But this will be 4y squared plus y to the 4th minus 4y cubed dy. Alright, and I will let y'all calculate from there. You should be getting 16 pi over 15. Now for example 5, we're going to be revolving about the line x equals 4. So this is going to be our first problem where we're not revolving about our x-axis or y-axis. And what this ends up changing is it changes how we calculate our radius. So let's go ahead and draw this out. Okay, so the first thing I want to note is that we have 1, 2, 3, 4. Let me mark these. This is going to be green, blue, and purple. So this is the line x equals 4. This is one of our curves that makes up our region. And we're going to be revolving about this curve. Okay, now here's what I want to key in on. Whenever you are revolving about the y-axis, right, whenever someone says y-axis, you need to know y-axis is the same thing as saying x equals 0. So what I want to say is that whenever you're revolving about some line that is x equals c, where this is just some real number, whenever you have something like that, you're going to have a dy integral, right? If we're using this washer disk method, okay? And that's because our slice is going to be perpendicular to this line. So we're going to need to do right minus left. Now, if you had x-axis is the same thing as y equals 0. So if you have something that looks like y equals c, where again c is some real number, you would have a dx integral. Okay? This would be a good thing for you to note down so that you can make sure when you're doing the washer disk method that you have the correct integral. All right. So let's put in our other curves. We should have y equals 0. So that's this curve right here. And then we should also have 2 square root x. So we'll have a point right here. We'll have one at, let's see, this is going to be 1, 2. We'll have another one. So let's see, once we get to x equals 4, this would be the square root of 4 times 2. So I need to go up to 4 right here. Put my point there. That might be the world's worst drawing of this function. It's okay. It gives us an idea of what this region looks like. It looks something like this. Now, we're taking a slice perpendicular to the axis that we're revolving about. That means our slice looks something like this. This point is going to be something that looks like 4, y. This point is going to be something that looks like x, y. So what we need to do here is we need to calculate the length of this segment. Well, here's a quick note. Any of these slices that we take, something like this, something like this, something like this, this, all of these, your x value is always going to be smaller than 4, right? We can tell that the x value lies to the left of 4 on our xy plane. So that means the x value is going to be smaller, which means we don't want to do x minus 4 because x minus 4 would give us a negative number. Instead, we want to do 4 minus x so that we get a positive number because our length should be positive. Or, well, it better be positive, not should be. All right. So we can say that the radius, right, so r equals 4 minus x. But we know that we're revolving around something that looks like x equals c, right? We have x equals 4. So we should have a dy integral, which means this radius needs to be in terms of y. Well, if we notice real quick, we have y equals 2 square root x. So what I can do is I can divide by 2 and then square it. So we'll divide by 2. We get y over 2 equals square root x. Now we'll square both sides, so we'll get y squared over 4 is equal to x. which means that our radius is equal to 4 minus y squared over 4. Okay? Now the next thing to note is, are we doing washer or disk method? Well, if we look at this, I'm looking right here up against our axis of rotation in our region. There is no gap here. Since there's no gap, that means we're doing the disk method. So we should have v is equal to the integral, right? We have a dy integral, so this is going to be our highest y value to our lowest y value. So this should be the integral from 0 to 4 of, let's see, so we should have a of x, which we know is going to be pi r squared. So it should be 4 minus y squared over 4 squared dy. Okay. From here, what you should be doing is pulling out this pi first off. And then after that, to calculate this integral, my suggestion is that you FOIL this out and then do your definite integral. When you do that, you should get 512 pi over 15. I highly recommend that you pause the video and calculate out these integrals. It will help you practice your integration techniques, okay? All right, now for example 6, first thing I'm going to do is note that we're revolving about the y-axis. Now I'll start drawing our region. So we should have, let's see, something that looks like, so we have green, reddish color, blue, purple. So we have x equals 0, which looks something like this. This also happens to be the axis that we're revolving about. I have y equals 0, which looks like this. I have x equals 2, which is going to look like this. And then x squared plus 1, that should look like, let's see, 1, four, 5. Okay, just barely going to sneak it in there. Okay, so this should be 1, 2, 3, 4, 5. Something that looks like this. Right, there we go, now I fixed it. Okay, and so then this is our region. And this will be the first time we use the washer method, because the purple line, or sorry, not the purple, the reddish line represents our axis of rotation. And we can tell that in between our light blue region and this axis of rotation, right in here, we have this gap. Not cap, gap. Okay? Since we have a gap, we're going to be doing the washer method, which, to remind you, right, so we know we're going to have a dy integral, but this should be the integral from a to b of pi times r out squared minus r in squared. All right, and then dy. So then the key here is to figure out, well, what is r out and what is r in? Okay. Here's an example of what R out looks like. It's going to be the space between, I'm going to start calling it like a maroon line. Actually, does this have a name? Plumb. Okay, we're going to start calling it plumb. Okay, so it's going to be the distance between the plumb line and, now this just sounds awful, between the plumb line and green. Okay, so the distance between the plumb line and green is going to be the distance between something that sits on x equals 0 and something that sits on y equals x squared plus 1. All right. Another way of saying that, this is going to be some point x comma y. This is some point 0 comma y. So the difference is going to be in the x values. So we'll want to do Rn is equal to x minus 0. So what we need to use, right, because remember we want things in terms of y, we need to use the fact that y, sorry about this, so we have y is equal to x squared plus 1, which means that y minus 1 is equal to x squared, which means that plus or minus the square root of y minus 1 is equal to x. Okay, so now we can rewrite our Rn as this is so we have plus or minus. Now, before I do this plus or minus will go away later because of the square. We can also, another reason we can get rid of the plus or minus is because this point, well, for one reason, this is a radius, right? This is a distance, which is going to be sitting in, which means that it has to be positive. So this should just be square root y minus 1. And the other reason is when we were looking at the point over here, this point is sitting in the first quadrant, which means that this x value has to be positive, which means we could have gotten rid of the plus or minus right here. Okay. Now let's calculate R out. So R out could be given by something that looks like this to this. Now notice the difference between the plumb line and the purple line is the same thing the entire time. This is going to be 2 minus 0. Okay. Which will give us 2. So then our integral looks like the integral from b to a, it should be volume equals the integral from a to b of pi times r out squared. So this is going to be 2 squared minus Rn squared. So this is going to be the square root of y minus 1 squared dy. Sorry, this was an a and a b. That looks awful. And our a and our b is our upper and lower bounds for y. So our upper bound up here is going to be 5, right? Because notice this is 1, 2, 3, 4, 5. And then the lower bound, right, we should say is right here, right? This is the lower bound for y. But I want you to look at something real quick. In here, right, at a point like what we've designated here, there's definitely a gap. There is a gap between the plumb line and the light blue region. However, look at right here. There's no gap here between the light blue region and the plumb line. When you see something like this where part of it has a gap and the other part doesn't, you need to break this up into two separate parts, right? What I mean by that is we're going to separate this into two parts like this, right? Divided at this line, where this is going to be the top region, and this we're going to call the bottom region. Okay, so this volume right here, I'm going to squeeze in here. This is going to be the top volume. And so since we're looking at the top volume, we're not going to take our lower bound all the way to this black point. Instead, our lower bound is going to be right here, because we just want to look at this top region, which means our integral is going to go from 1 to 5. Okay, so then this is going to be pi times the integral from 1 to 5 of 4 minus, so now we can cancel out our square root because we're squaring it. So this is going to be 4 minus y minus 1 dy. And then y'all can calculate from here what our answer would be. You should get that the volume of this top region is going to give us 8 pi. Now we need to look at the bottom region. Okay. So now looking at the bottom region, there's no gap there. Sorry, I didn't write that in earlier. No gap. So we should have a disk, which means we should have v equals the integral from a to b, our upper and lower bounds for y, which would be 0 to 1, of a of y dy. And so this is going to be the integral from 1 to 0 of pi r squared dy. Well, the radius here isn't bad to calculate. It's just going to be this radius right here, which would be 2. So this is going to be pi times the integral from 1 to 0 of 2 squared, which is 4, dy. And so we'll get that this bottom portion has an area of 4 pi. Sorry. When we revolve it around our axis of rotation, it has a volume of 4 pi. And so then in total, we will have a volume of 8 pi plus 4 pi, which will give us 12 pi for our total volume. Okay, so you need to make sure that when we get a picture like this, you're considering all parts of this light blue region, right? If all of it is away from our axis of rotation, then we can just do a washer setup. If all of it is shoved up against our axis of rotation, then we can just do a disk setup. Now, there are times where we are not going to do either one of those because it turns out it becomes incredibly difficult. But at that time, we will introduce a new method called the cylindrical shells method. That will be in the next video. Now let's look at example 7. Example 7 asks us to revolve about the x-axis. Right, we're going to have green, plum, blue, and purple. Okay. What I'm going to do is I'm going to rewrite this plum equation so that I have something that looks like y equals mx plus b, because something like that, I know what it looks like right away. So I'm going to rewrite this as y equals 1/2 x plus 1. Okay. Let me go ahead and mark my other lines. Okay, I've got x equals 0, y equals 1. We're going to have y equals 1/2 x plus 1. So that means I should have a y-intercept at positive 1 with a slope of 1/2. So that means I go up 1 and over 2 every time. Okay, so some line that looks like this. And then we'll have x squared plus 2. And so that should look something like this. And so then my region is going to be this region in here. Okay. So what I need to do here is I need to decide washer or disk. Well, the one thing I forgot to do was to mark what we're revolving about. We're revolving about the x-axis, so we're revolving about this black line right here. And we should notice right away that there is this gap in here. Now we have a gap between our entire region and our axis of rotation, which means this is just going to be all one big washer method. Okay. So we should get, well, let's calculate R out. So R out is going to be something that looks like this. So that should be the difference between the green curve and the x-axis. So we're going to have R out is equal to the difference between the green curve and the x-axis. So that's going to be x squared plus 2. Whoops. Minus 0, right? And so that just gives us x squared plus 2. I'm using the green on the x squared plus 2 to show you where that's coming from. It's coming from that green curve. Okay. Then Rn, right? This would be the inner radius. So something that looks like this. Okay. So that's going to be the difference between the plumb line, which is given by 1/2 x plus 1. And then we take the difference between that and the x-axis, so minus 0. So we just get 1/2 x plus 1. All right. So then we should have our volume is equal to the integral between our bounds. So notice our bounds, we go from the origin, which has an x value of 0, to this x equals 1 line. Okay, so this is going to go from 0 to 1 of, let's see, we should have pi times r out squared. So this is going to be x squared plus 2 squared minus rn squared. So this is 1/2 x plus 1 squared and dx. Okay, and then this should be, so I don't have any tricks here except for pull out pi, FOIL these both out, combine like terms, and then integrate. And when you do that, you should get that this is approximately 12.41. Okay. Moving on to the next example, we're going to be finding the volume of the solid obtained by rotating the region bounded by the following equations about the x-axis when y is less than or equal to 3. Okay, this is a lot to take in, so what I'm going to do is try to get our picture going. So first thing I note is we're revolving about the x-axis. Okay. So we're revolving about this axis right here. And we have y equals x squared plus 2. So that looks something like, let's see, we should start off with a y-intercept of 2. I guess I should mark these first. I'm going to use that plum color as little as possible because I hate using that word. I just, for some reason, don't like it. Okay. I should get points here and here. I'm going to go one further, 2. So that'd be 2 squared, which is 4 plus 2, so 4, 5, 6. Oops. It looks something like that. Then I'm going to have y equals 3x. Okay. So it starts here. Ooh, and then it goes up to here. That's a nice intersection point. And then it would go up to, let's see, 1, 2, 3. So it'd go up to here. Right, so it looks something like this. And then, let's see, we also have x equals 0. Right, and we need to be looking at when y is less than or equal to 3. So I might as well just go ahead and draw in something like this. So now we're looking below this dashed line. But I think we can do it without that dashed line. So looking at when we're below that dashed line, when our y values are less than or equal to 3, the area bounded by these 3 regions is going to be this light blue region in here. Okay, so we're going to be revolving that about the x-axis. So what I noticed here this entire time is that we have what I mean by this entire time, the entire time along this light blue region, we have a gap. And so that tells me that this is purely going to be a washer method. Okay, so now I need to calculate my R out. And since we're using the x-axis, we should have a dx integral. So let's see, we should have R out is equal to, well, let's see the green, which would be x squared plus 2 minus, let's see, we're on the x-axis, so that's going to have a y value of 0. And then Rn is going to be equal to, let's see, Rn would look something like this. So it's going to go from the blue line, which is 3x, minus 0. So this is just x squared plus 2, and this is just 3x. So then we should have that our volume is equal to the integral from 0 to 1, right, our lowest and biggest x values in this region, of pi times r out squared, so x squared plus 2 squared, minus Rn squared, so 3x squared dx. And this should give you 38 pi over 15. All right. Moving on to example 9, we're going to be using the same region as example 8, but we want to rotate the region about the y-axis. So this is actually going to cause a problem for us. The reason being, let me draw our graph again. The graph looked something like this. Let's see, we had this. We had a purple line. we had a beautiful green line that intersected here. I'm not being precise about this at all. All I want to note is a few things. That I want this to look clear, so maybe I should... Let's make this intersection point up here. Okay. You can draw this out more exact like we did in the last example, but the main things to note is kind of like what's on top, bottom, left, right, stuff like that. And then also what these points are. So I'm going to go ahead and mark what these points are. This was supposed to be the point 0, 2. This was the point 1, 3. And then this was the origin right here. This black circle point. Okay. So if we're rotating about the y-axis, then we get a problem we've seen before, which is we need to break this up into two separate intervals. Because here we have no gap, which means this is going to be a disk, but here we have a gap, which means that top portion is going to be a washer. So let's look at it. Top. Okay, so we need to calculate our R out, which is going to be the difference of the X values right here. Right. Now, the issue is that when we started this problem, we weren't given, X equals stuff. We were giving Y equals stuff. Particularly, we were given Y equals X squared plus 2. And we were also given Y equals 3X. Well, we'll get X alone in both of these. So I'm going to subtract over 2 and then take a square root of both sides. And then over here, I'll just divide by 3 on both sides. And so now I've got everything in terms of X equals, nothing but Y's and constants and stuff like that. So I can say that R out is going to be, well, let's see, the X value of the green curve. So that's square root Y minus 2 minus 0. And then we'll have Rn is going to be Y over 3. Sorry, so this is a bad representation to use as our red line because this is at a point where the green and the blue are meeting. Instead, let me take a red line that looks like this, and you'll see that the red line actually goes past the green line to the blue line. So our R out should be blue minus, I guess you could really say this is purple, right? Because purple was X equals 0. So this is minus 0, this is minus 0. And then this one should have been Rn, right? We can see that by this. This is our inner radius, and it only goes to the green curve. Okay. So this will be square root Y minus 2. This will be Y over 3. So then our volume is going to be given by, so V equals the integral from, let's see, so the top, which was, the top integration limit should be 3. That's what we have here. And the bottom integration limit should be 2. That's what we have here. Okay? And then it should be pi times R out squared. So Y over 3 squared minus Rn squared. So that would be square root y minus 2 squared dy. And when you solve that, you should get 11 pi over 54. Now for the bottom, that's going to be a disk, right? This region right there, that's the bottom. And so the radius on that is just going to be the distance between the purple and the blue line, which we already know is y over 3. So since there's no gap there, we're going to be using disk. So that should be the integral from 2 to, we're going down to the origin. So we're going to be doing the integral from 0 to 2 of our a of y formula, which is pi times the radius squared. Well, our radius is the distance between the blue line and the purple line, which is given by y over 3. And so then we have pi r squared right there, dy. And when you integrate this one, so this one's a little bit nicer to integrate, right? We can square this, we get y squared over 9. We can pull out pi over 9 as a constant, and then this one's a lot nicer to integrate. And so this one will give you 8 pi over 27. And so this is an example of when my total volume, I would not simplify it anymore. I would just say that volume is equal to 11 pi over 54 plus 8 pi over 27. Yeah, it's not too bad. I can multiply 8 pi over 27 by 2 over 2, and then we'll just have one fraction as our answer. But there's really no reason to do it. This is a perfectly fine answer. This is for calculators to take care of afterwards. Okay, now let's look at example 10. So the motivation now is that we have example 10 and then example 11, and then we'll be done. Okay, so for example 10, we can set up our region by doing the following. So we're going to be rotating about the line y equals -1, so that'll be a little interesting. But we should have this green line y equals x, and this blue line y equals x squared. Now, I know from past experience with these curves that they can look very similar, right? What I mean by is, like, when we're in between the interval from 0 to 1, their values are pretty close to each other. And what that means is that the region between the two is going to be pretty small. So I'm going to choose some different, I guess you could call it like different intervals on our x and y axis. So I'm going to call this 0.5 and this 1. Right? Normally each tick mark counts as 1, and that's what we normally do. But from past experience with these, I kind of know that it's going to be better for us to break it up by 0.5 and 1. And on this line, I'm even going to do 0.25, 0.5, 0.75, 1. Okay. So my y equals x line, we should have 0, 0.5, 0.5, and then 1. We get some line that looks like this. My blue line, we should have the origin. Now, if we plug in 0.5 for x, we should get 0.25. And then, when I plug in 1 for x, we should get this right here. So what we get is something that looks like, and see, now this is messy because I'm not exactly going through these points, right? But this is kind of what our region looks like. So you can tell like how slim it would have been if I just went by ones, and it'd be hard for us to tell, top and bottom, stuff like that. Basically in this, what's going to matter here is our RN and our R out. Even though we haven't necessarily discussed that we're doing a washer yet, but spoiler alert, we are. Alright. Now the reason we're doing a washer is because we're rotating about the line y equals -1. That's this line right here. So we're rotating about this. There is most clearly a huge gap. Okay. So what we need to do is we need to use our washer method. Well, remember, we should always be taking our slices, or in this case, our radius, perpendicular from our axis of rotation. So here will be an example of our RN. Here's an example of our R out. These are nice examples where I can kind of write something out like this. Oops. All right. RN, R out. Okay, so we've decided we're doing washer. We've identified RN and R out. And let's look at how we calculate those. So R out is going to be the difference between the green and the orange. Let's call it orange. It looks like orange. Orange curve. So this should be, and also we notice that we're revolving about y equals -1, which means that we should have a dx integral. Okay, so which means we're going to want things in terms of x's, which is good because they were given to us in terms of x's. So we're going to have the green curve, which was x, minus the orange curve. Now normally we've been writing -0 because our thing that we're rotating about is normally the x or y axis, which are, x equals 0, y equals 0. So that's why we've been writing -0. Now our axis of rotation isn't something like x equals 0 or y equals 0. So we're going to have minus -1 because we're revolving about y equals -1. So this should be x plus 1 for our R out. Now our R in, we're going to have blue minus orange. So this should be x squared minus -1. So this is x squared, whoops, I don't want to use that color, x squared plus 1. So then my volume can be calculated by the integral from, let's see, our leftmost x bound, which is at the origin, so that's 0, to our rightmost x bound, which is at 1, so this is 1. Okay, and so then this should be pi times R out squared, so this is x plus 1 squared, minus R in squared, so this is going to be x squared plus 1 squared. And just as usual, my suggestion for calculating this integral is FOIL both of these out, and then combine like terms, pull out the pi, and integrate. And when you do so, this should give you 7 pi over 15 for our volume. And so this is a pretty small, so I was saying that the area of this region would be small, right? And so since we're rotating and creating a solid, the volume's going to be a little bit bigger. But even if we think about this, this is something like 7 times 3, which is 21 over 15. So to get an idea of how small this region actually is, think about, even though we're rotating and making a solid, its volume is approximately 1. Okay? Now, example 11. Example 11 is going to be another fun one, but we'll make it through it. So, example 11, we are graced to have the opportunity to revolve about x equals -3, which I'm sure will be a joy. Make this x-axis a little bit better. Okay, so we're going to have green, not plum, and purple. All right, so we have x equals 0 as one of our axes. I'm so glad we're on the last problem because I think my drawing is getting exponentially worse as we go on. Okay, then we'll have y equals x cubed, so we'd have like 1, 1, 2. Okay, this gets real fun real quick. 2, 3, 4, 5, 6, 7, 8. I'm cheating at this point. I don't need a pretty graph that's going to win an award. I just need something that is going to get us through the problem, get us a good idea of our outs and our in. Okay, and then we have 2x plus 4. We've got a y-intercept of 4. Oh, great. Okay, so I'm going to cheat and bring that down a little bit. That goes right there. Then our line looks like this. Okay, so the lesson to be learned here is maybe think ahead of time of how big these values are going to get, right? So remember how that other graph, I knew that the difference between x and x squared was going to be pretty small. So instead of incrementing by 1, I started incrementing by 0.25. I should have known here that x cubed, while we're cubing it, it gets big rather fast. So maybe I should have incremented things by 2 instead of 1. But we get the idea. This is our region. Okay, and then we're going to revolve about x equals -3. 1, 2, and just to get it out of the way of that blue line, 3. Okay, so here's our line that we're revolving about. Whoop. Okay. There is 100,000,000% a gap here the entire time. However, let's look at this. I think we can agree that the purple line, no matter where I draw my slice perpendicular, right? So what I mean is I can draw a slice perpendicular here, 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 right? Keep going forever. No matter which one I'm drawing, I always hit our region on the outer point. Sorry, let me word this better. When I stop my line, okay, that's not going to work if I don't stop my line at the right place. When I stop my line, I'm always stopping on green, right? So it's always going to be, green minus orange for our out, right? Our outer radius, the bigger radius. However, notice that my inner radius for these lines is here. However, my inner radius for this top red line is going to be here, which means that my inner radius is changing. And where it's changing is right at this area right here. So what I'm going to do is take this red stuff away. Okay. And this tells me that I'm going to need to break this off into 2 separate regions right here. Right, and this was right at y equals 4. Good. Okay. So we'll separate this into top, top and bottom. All right, so let's work on top first. We still have a gap. We're still using washer method. We know that our out should be, this is not route, this is r sub out, is going to be equal to green minus orange. Right? An example of that is right here. Green, orange. So this should be y equals x cubed. Right, so this is going to be x cubed minus, this should be -3. Now, before I get going too much on this, we do need to notice we're drawing our line perpendicular to x equals -3, right? So we should have a dy integral, which means that this r out needs to be in terms of y and not x. So what I'm going to do real quick is we have y equals x cubed. I'll cube root both sides. Oops. Sorry. I just want to cube root both sides, so let's cube root y equals x. So this is y to the 1/3 minus -3 will give us y to the 1/3 plus 3. Okay, and that will give us our outer radius. Now for our inner radius, let me go ahead and make the adjustment. We have y equals 2x plus 4. So I can subtract over 4, divide by 2. So that means we get 1/2 y minus 4 divided by 2. So minus 2 equals x. So we should have that Rn is equal to, right, so that's going to be something like this, where we have blue minus orange. So this is going to be 1/2 y minus 2 minus orange, so minus a -3, which gives us 1/2 y minus 2 plus 3, so plus 1. Okay, now we can calculate volume. We get that volume is equal to the integral. All right, our top y bound, remember I squeezed that in earlier. This was 1, 2. We do y equals 2 cubed. That's going to be at 8, right? This has a y value of 8 up here. That's our upper limit. And then this goes to y equals 4. Good thing we wrote that down earlier. Just kind of a little predict the future type moment. So this is going to be pi times the outer radius squared. So we have y to the 1/3 plus 3 squared minus inner radius squared. So this is y over 2 plus 1 squared dy. And when you calculate this radius, or sorry, this volume, you should get approximately 85.6. Okay. Now for the bottom, we should have, remember we said that the outer radius was going to stay the same the entire time. So I can go ahead and write that down. I'm not going to use different colors or anything. That's just going to be r out equals y to the 1/3 plus 3. But what we need to calculate is our new inner radius. So this is going to be Rn equals, okay, so if I do an inner radius here on the lower region, notice it's going between these two, so it needs to be purple minus orange. So this will be 0 minus -3, which will give us 3. So then the volume here should be the integral from, let me go back up. This is going to be from 4 to the origin, which is 0. Or sorry, I should be saying from 0 to 4 of pi times, this is y to the 1/3 plus 3 squared minus, okay, just 3 squared dy. And when you calculate this, you should get approximately, sorry, I'm not going to put equals, approximately, that's what this little double tilde symbol means. It means approximately, not exactly equal to. So approximately 108.76. And so then our total area, our total volume, is going to be 85.6 plus 108.76. Is approximately. Since these are two approximations, this is still an approximation. 194.36. Okay? That will conclude our volumes, and then next time we'll learn about when we have something that looks crazy and really difficult, how can we use this other method to make it not super crazy and super difficult. Okay, and now at this point you have reached the end of the material that you need to cover for Wednesday's class activity, which means you can continue to watch 6.3 and 6.4 if you'd like to, but those will be for Friday's class activity. So just make sure that you understand this material really well, and you will be ready for Wednesday's class activity. So maybe go try some homework problems, some quiz problems. Maybe don't do anything that you have to submit, right? So maybe try a homework problem. If you get it wrong, maybe try a different one, but don't use up all 3 of your submissions, because you can kind of use Wednesday's class activity to get maybe a little bit better understanding of the material.